Our webinar will start momentarily. Welcome to this edition of the Great Designs in Steel technical webinars. Thank you for joining. My name is Brian Esterberg. I'm the Senior Automotive Market Strategist at the American Iron and Steel Institute. And today we're pleased to welcome our guest speakers, Dr. Yu-Wei Wang, Advanced Engineering Corporate Manager at Cleveland-Cliffs, and his associate, Miao Yu, Advanced Application Engineer. They'll be expanding on its introduction and exhibit at Great Designs in Steel in May and review design and testing of the CCBE steel battery enclosure and C-STAR steel tube and reinforcement designed by the advanced engineering team at Cleveland-Cliffs. For today's webinar, your microphones have been muted. Please use the Q&A feature in Zoom to submit questions throughout the webinar. We will not be using the raised hand or chat feature today. Again, use the Q&A feature and submit questions throughout. My colleague Hisham Hazat, our Senior Technical Advisor, will join Yu-Wei to address questions following the presentation. And a copy of this presentation will also be made available on demand following today's webinar. At this time, it is my pleasure to welcome Dr. Yu-Wei Wang.
Thanks, Brian, and good morning, everybody. Let me share my screen first. Yeah. Can everybody see my screen?
Looks good, Yu-Wei.
Okay, great. Yeah, again, good morning. First, just a few words about Cleveland-Cliffs for those of you who are not familiar with us. We are vertically integrated steel producer from iron ore to different steel mills across the Midwest. You can see at the bottom of the screen that our extensive product offering. We produce electrical steel, stainless steel, to carbon steel, which ranges from mild steel all the way to Gen 3 advanced high-strength steel. We also have downstream operations of tooling and stamping, as well as tubular component. Our group, a couple words about us, is at Advanced Engineering. Under Application and Advanced Engineering Group, we're part of the Research and Innovation Center, headquartered in Middletown, Ohio. The primary task of ours include the material characterization using different testing, standard test, as well as the customer's test. So we also conduct CAE modeling of structure performance, and as well as stamping feasibility, working with CTS, Customer Technical Service, to troubleshooting root cause for the stamping issues at the plants of our customers. So in recent years, our group has been focusing on developing innovative steel solutions at a competitive cost. And the C-STAR and CCBE are two of the products we have developed recently. And both of these have been presented at Great Designs in Steel, C-STAR at 2023 and CCBE at this year, so both by mail. So I'll let Mel talk about the C-STAR first, and then I'll help him out with the CCBE. So with that, Mel, it's yours.
All right, morning, everyone. Thanks, Yu-Wei. So firstly, appreciate for attending today's webinar, and I will run through the Cleveland-Cliffs steel tube as reinforcement together with you guys. So firstly, battery electric vehicles are roughly 20% heavier than the similar size of internal combustion engine vehicles, which will bring more challenges for the crash. And one of the major crash load case is the side pull. So this load case will cause a significant deformation on the battery enclosure and leading to some safety concerns. So on the left-hand side, we have the comparison of some rocker structure between S vehicle and BEV. Firstly, in longitudinal directions, we can see that the rocker reinforcement for S vehicle covers the first row, and several of the stiffener brackets are placed at optimal positions. However, for BEV, the rocker reinforcement pretty much covers all the area from hinge pillar to rear wheel housing. And in longitudinal directions, the stiffeners or the brackets, they either extend from top to bottom or they attach to rocker inner and rocker outer. For BEV, the reinforcement extends all the way from inboard to outboard, and this almost occupy the whole space of the rocker. So in summary, for both longitudinal and the lateral directions, more material is needed for BEV due to the energy absorption as well as the intrusion protection. To overcome the challenges, we come up with the C-STAR design. We know that long, uniform, and hollow design space is ideal for tube design, and the multi-chamber shapes are pretty effective for energy absorption as well as the lightweighting. So our C-STAR is really a versatile, scalable solution for structure reinforcement. Here we list the two C-STAR design. The design number one, we have 3 tubes laying as a line, and the different color means various combinations of gauges and grades. And for design number 2, we have a different stacking type. So you can see 2 tubes, they are stacked vertically, and another one is attached aside. So our C-STAR is developed to compare against with aluminum baseline here, especially the design number 1. They have the same weight, which is 90 millimeter, and on the height wise, we are 27 millimeter, which is shorter than aluminum. This means we need less packaging space. So the gauge is 1.8 millimeter and grade is 1500 for our latest C-STAR design. So I do want to mention that our preliminary C-STAR design number 1 is 1.2 millimeter with the DP780. But that one is much lighter than the aluminum baseline. So we update the material gauge and grades to have an apple-to-apple comparison. The tubular components will be the facility to make the tubes. So we are the leader in advanced high-strength steel tubular solutions and the makers of FORMTUBE. We have the widest product mix in electric resistance welding market. We can do carbon stainless, and for carbon from mild steel to Gen 3 advanced high-strength steel. And for the coated, we can do GI, GAEG, aluminized, and of course, uncoated. We have the unmatched ERW dimensional capability. From thin gauge to thick gauge, small diameter to large diameter, 100 to 1 D to T ratio, this is really the capability that distinguishes us from other tube makers. We can also achieve a superior tolerance control. And for the twist, we can maintain 2 degree over 2 meter length. And for the straightness, we can have a 2 millimeter tolerance over 2 meter length. So here are several examples made by our tube. And as you can see, not only the common shape like rectangle and round shape, we can also make the super customized shape, the peanut and the oval, and of course in different gauge and grades and D to T ratio. So once we have the tubes ready, our partner TWB help us to weld them together. And they specifically designed the fixture for these applications. And the quality of the weld has been checked by macro etch. So we noticed that the penetration is more than 3 times of the thickness. This means a very robust connection, and the weld strength passes the rupture test, which is shown in this picture. So we use the three-point bending to assess the performance. The test setup is very straightforward. We have the anvil in the middle and the supports on the sides. This anvil is speed controlled, force displacement data is collected, and of course, we do evaluate the peak force and energy absorption. So we use this Zwick Royal HTM testing machine for this purpose. The machine can do from low speed to high speed and is capable of 160 kilonewton nominal force. Now let's take a look at the test results. This is a comparison of our C-STAR and aluminum test. The left-hand side shows the C-STAR results. The right-hand side shows aluminum test. For C-STAR, as I said, we are 1.8 millimeter with PHS 1500. It weighs 2.2 kg. The peak force is 143 kilonewton. For the aluminum, it's 4.6 millimeter, 6000 series. It weighs 2.0 kg. The peak force is 107 kilonewton. So for C-STAR, we can see the indentation on the contact area. However, the overall structure maintains the integrity after the test. And we can tell from the both the video and deformation picture that after the test, there's a crack across the whole section of the aluminum baseline. So this makes it lose the capability to maintain more load due to the characteristic of the material. Now let's take a deep look at the force and energy absorption of two design or of the two testing samples. So left y-axis is the force and the right y-axis is energy absorption. The green lines, they are the C-STAR design, and brown lines are aluminum baseline. And all the solid lines, they are force. All the dashed lines, they are energy absorption. So first, let's take a look at the force. From 0 to 17 millimeter, the two force lines, they are very close to each other. And after 17 millimeter, steel start to outperform aluminum. For the value-wise, the C-STAR peak force stays at 143 kilonewton of 50 millimeter. And for the aluminum, it's 107 kilonewton at 17 millimeter. So we are 30% more than the aluminum on the peak force. And for the energy absorption, from 0 to 33 millimeter, these two dashed lines, they are tangled with each other. And after 33 millimeter, where the crack in aluminum propagates across the section, the energy absorption line goes flat. However, our C-STAR still builds up energy very quick. So in conclusion, from 0 to 33, we are close, and C-STAR is very competitive to aluminum baseline. And after 33, C-STAR outperform aluminum. Besides the component level, we also check the subsystem level performance. So factors like peak force during crash event, energy absorption of the rocker structure. So not only the reinforcement, but also the rocker inner and outer, and energy of battery structure and deformation of battery structure members, intrusion, deformation of the rocker space. All of these factors will be evaluated under the subsystem level, and this will be helpful for us to understand the behavior of the system under vehicle level perspective. So combined C-STAR with CCBE, which we will talk about, will provide the superior protection to the customer. All right, now let's hand the steering wheel back to Yu-Wei.
Yeah, thanks, Mel. So now let's take a look at the CCBE. Again, Cleveland-Cliffs Battery Enclosure. So we know electrification is the future of the automotive industry, and battery enclosure as a power supply unit is one of the most important components in the BEV. Our design is a steel-intensive battery enclosure with efficient design for minimum cost and weight while meeting performance targets. It is designed as a cross-utility vehicle, but can be scaled to fit any unibody architecture. As shown on the top right, 8 battery modules are bolted to the cross members with 104 4680 type batteries in each of them, giving us the power of 80 kilowatt hour. As shown, the size of the battery enclosure is about 2 meters long, 1.5 meters wide, and 150 millimeters height. CCB is connected to the vehicle body through 2 side rails, as well as 6 bolts in the middle of the battery pack. So now let's take a look at the details of the design of CCB. It is a really simple design, and with top cover stamped using mild steel as number 1. It has longitudinal cross members, number 2, longitudinal stiffeners as 2 of them, number 2, and 1 longitudinal members, number 3. It has 5 cross members, as shown, number 4. And these cross members, longitudinal and lateral, using advanced high-strength steel magnetic 1500 and the multi-phase 980 that give us excellent impact protection as well as achieving the minimum weight. For the number 5, it's 2 external rails made of ultralium 1500 tubes. Its unique design provides excellent side impact, and at the same time, it is used to connect the battery enclosure to the body structure, to the rocker panels. And the last, number 6, is a one-piece stamped tray using tailor welded blank. As can be seen, it's a combination of magnetic 1500 in the middle of the bottom of the tray, and mild steel the rest of them. So for the design validation, for manufacturability, we have successfully stamped both the top cover as well as the tray at our partner EMI. For thermal runaway performance, our partner Technical has conducted an extensive series of component level tests, which I'll show the results, share the details, some of the details. And for structure validations, we have conducted multiple CAE modelings, evaluating the underfloor and side impact performance, as well as drop test, shock test, and the model analysis. So first, let's take these are the 2 pictures taken at the site of EMI, and the lower right corner shows the press and press and die used to stamp these panels. And the one on the left with Argus grade on it, so the color looks a little bit different. But anyway, so the key for this design, for this tailor welded tray, is the design of it. So as you can see on the top left corner, it is a pong-shaped tailor welded blank design with magnetic 1500 in the middle and mild steel around it. And this enables us to not only avoid any stamping failures, but also maintain excellent shape control. On the left-hand side, so formability results, simulation results of formability and the thinning. On the right-hand side, Argus results measurement of the actual tray. As you can see, the most of the deformation occurs at the corner, and then with left and right, modeling and prototype have a very good correlation. For the as I mentioned, this pond-shaped unique design of the tailor welded blank enables us to achieve excellent shape control. And we also conducted flatness measurement UCMM, both the bottom of the tray as well as across the flange of the tray. And we achieved excellent flatness on the across the flange, plus minus 1.5 millimeter of the entire flange. So we passed our target. So this flatness of the flange is a key to prevent the leak. So for us to meet the leak test target. And this one shows the configuration setup of the leak test. So the tray is placed in the test tank upside down and clamped on the fixture. Tank is then filled with water to submerge the tray, and the tray is pressurized internally to 2.5 psi. So besides the flange flatness, laser wire line was also a concern, a point of concern that may be a potential source for leak. So as you can see from this test, both the flange flatness as well as the laser wire line passed the test. So meet the requirement of leaking rate less than 15 standard cubic centimeter per minute. And then we passed the test with a flying color. As for the structure performance, as I mentioned, we conducted multiple CAE analysis. Here I'll just give you two examples. One is the side impact. The other one is ballistic protection. So this one shows the setup of the computer model to simulate the side impact, side pole impact. As you with animation of the stress contour. As you can see, from the color of the stress map, most of the shock are taken by the side rail, which is made of ultralium 1500 tube, as well as the cross members made of multi-phase 980. So there's no touch to the battery, meeting our target of no touching to the battery module before the load reaches 100 kilonewton. And this one shows the setup for the CAE model to simulate the underfloor impact. As you can see, the 20 millimeter diameter pole is placed at the weakest location. This is between the two cross members, as well as the longitudinal cross member and the longitudinal stiffener. So this is in the middle of nowhere. And then we also place evaluate the situation as number 2, place the 20 millimeter pole right under the cross member. So both cases pass our design target of no touching of the battery module before the load reaches 35 kilonewton. So for the thermal runaway test, our partner at Tenneco have conducted a series of component level tests. On the top shows the setup for the abusive torque test. Our solution of using the steel with Tenneco's Protex 7040 and 7045 provide excellent thermal runaway protection. No burn through in 15 minutes. And with the backplate temperature, it's around less than 295 degrees centigrade at 15 minutes test. So outperform the current solutions as shown on the left. Yeah. And then this one shows the results of testing under 15 degrees centigrade. As I forgot to mention, the previous test was conducted at 1500 degrees centigrade. This one is at 1000 degrees centigrade for 10 minutes. So it's a test of different combinations of different steel with different coating, different gauge with Protex shield 7040. As you can see, all the tests provide shows excellent results with the backplate temperature no more than 185 degrees. Also, from the chart, as you can see that the gauge has a positive impact. With a thicker the gauge, the better the performance. And however, the coating, it does not seem have a significant impact on the result. As I mentioned again, Tenneco has performed a series extensive tests. So anyone's interested in a contest, we can provide the details. So in summary, C-STAR is a highly configurable and scalable product that provide superior protection for battery as well as the occupants, with advantages of cost efficiency and ease of manufacturing. Cleveland-Cliffs Battery Enclosure is a sustainable and robust steel solution that utilizes an innovative one-piece bottom tray stamped with a laser welded blank that passed the flange, flatness, dimensional requirements, and the leakage test. So for current joint development, we are working with multiple OEMs and Tier 1 customers to develop C-STAR and CCBE that fit their design space and meet their performance, mass, and cost targets. Those projects are at various stages of prototype build, full vehicle validation, and near commercialization. So as always, we stand ready and happy to work with all our customers to jointly develop design, CE optimization, and to prototype, use the extensive capability of tube making of our tubular component group, and also conduct component level validation of through testing. So with that, I can take some. We can take some questions. So thank you for your attention. Hassan, you muted, Hassan.
Am I coming through?
Yep.
Okay. Well, just thank you very much for a great presentation. I think the topic is really timely when you come to think about the state of the automotive industry and electrification. I do have some questions coming from our participants, so let me go ahead and share those with you. The first question is: are the tubes joined together using a continuous laser weld, or is it a laser skip weld? And I think this is referring to the rocker reinforcement.
Yeah, it's a good question, Hassan. Yes, they are joined through a laser weld, continuous throughout the length. But however, our test, we evaluated different laser pattern, stitch weld. Our preliminary results show that as long as you have between 50 to 70% of weld, the performance of three-point bending for energy protection does not change significantly.
Okay, great. Another question related to corrosion. It says, what type of corrosion protection are you using, electrogalvanized or GI?
Now we use the coating material, but with different target applications, we can use other like e-coat or powder coat and stuff like that. So each of the application could be different. Yeah.
Okay. There's another question specifically again related to welding. It says your battery tray design has welds, and it has been reported that a lot of the auto OEMs do not like welds in their battery trays. So how do you propose that this design will go with the OEMs?
So our joining method right now, we use combinations of bolt, weld, and adhesive. So those are depending on the specific applications. So there are some alternatives. We can evaluate the details per different applications. Yeah.
Okay, that sounds that sounds reasonable. So this is a follow-up question. I think you've just answered it, but we'll go through it anyway. So besides the laser welding, what other joining processes are you using in the manufacturing of the battery tray? So I think you just touched on that, but maybe you want to emphasize this one more time.
Yeah, so we do have conducted extensive study using adhesives that depending on your target of structure performance, those are very efficient joining method as well. But yeah.
Okay. There's a question. Yeah, go ahead.
Sorry, Hassan, did I understand right? They were talking in general or talk about the laser welded, the TWB tray?
It's what other joining processes used in the battery tray manufacturer. So I'm assuming that, It's a general,
Battery enclosure. Okay.
yeah, for the whole battery tray, yes.
Yeah.
There's another question about how are you fastening the ultra-loom tubes to steel?
We use both weld and bolt, yeah, for the
Okay.
side rail, yeah.
What kind of G-forces were measured in the impact test, especially at the point of impact? Did you measure the G-forces at the point of impact?
To just clarify, we did not do physical test for the
Okay,
side impact
okay.
test. It was just a computer simulation
Yeah.
to assess the performance. As I mentioned, we have external side rails made of 1500, ultra 1500, as well
Yeah.
as very cross members made of advanced high strength steel. So we have kind of 2 layers of defense.
Okay. Yeah, I suspected that would be the answer. This one is a kind of a long question. Let me read it to you. First of all, it says very interesting work. Thanks for sharing. And in the CAE impact validation models, was it done using explicit or implicit analysis? And did the material model consider strain rate dependencies and or damage models?
Yeah, we use the damage models and we use the explicit method. Yeah.
Yep.
Yeah, we did not consider the strain rate. Yeah. However,
Okay.
we do have the strain rate information available. If anyone is interested, we can share their results. We can actually also kind of redo some of the analysis if they are concerned of the impact of that. So.
Yeah, for all intents and purposes, I would believe that it would be more positive anyway. So
Yes. Yeah.
Yeah.
You'll be better performance. Yeah.
Exactly. Yeah. Another question: how did you determine the equivalent thickness of the C-STAR steel grade as compared to the aluminum? I'm assuming that. Let me just go back. Yeah, as compared to the aluminum. For apples to apples comparison.
So we evaluated from the total mass, total weight, as opposed to the gauge. So apparently, our C-STAR steel tube gauge is much thinner than the aluminum. But the example Mel presented that we are about 10% heavier, but our performance is much higher. So we can actually just make a prototype for the purpose of A to B comparison, exact mass. But and we expect the similar result. Yeah, we are from at the mass parity. Our performance is better than the aluminum design. Yeah.
Excellent. Okay. So it was really a mass to mass.
Right.
Okay. Very good. Reasonable. Another question: what press tonnage is required to stamp the tailor welded blank tray?
Yeah, it's enough. It's about 2,500. So around for the tray. Depending on the configurations of tailor welded blank design, so ours is 2 millimeter, 1,500 plus mount steel. Yeah.
Okay. For the C-STAR structure made of PHS, did you evaluate the susceptibility to hydrogen embrittlement, or is there susceptibility to hydrogen embrittlement?
We have not looked into that yet, so that definitely needs to be. We could look into that if that is a concern. Yeah.
Yeah, on a case-by-case basis, I assume.
Right.
Absolutely. Yeah.
And yes, Hassan, right. And I just want to point out that we Cleveland-Cliffs offer a wide range of product, and this is just one of the grade that one of our customers is interested. We can look at other alternative grade that. Where you have a less of this liquid metal embrittlement concerns. Yeah.
Yeah. There's a question here about the C-STAR again. Are you starting with circular tubes and then hydroforming, or are you just basically starting with square tubes, or how do you get there?
Our tube, we have, as Mel mentioned, we have Cleveland-Cliffs has a subdivision called Cleveland-Cliffs tubular component, CCTC. Their tube are made of ERW method, and then we started with round, and then they shape it and reshape it to different cross sections. Yeah.
Okay, very good. I think you've answered this one. It's really, again, related to the type of press. So it says, what size type of press are you forming the tray on? Is it mechanical or hydraulic or servo? How much pressure is required? I think you've basically answered some of that before.
Yeah. So the tray, as I mentioned during my presentation, was stamped. Both the top cover, which is made of 0.8 millimeter mild steel, and the bottom tray, tailor welded blank 2.0 millimeter mild steel versus magnetic 1500. So both are stamped at our partner EMI using a hydraulic press.
Okay. Related to the thermal testing, the question is your thermal runaway temperatures for simulation an accurate temperature for battery arcing, or these temperatures you tested to?
Yeah, that's a good question. So the result I presented today, conducted by Pinnacle, our partner. It was conducted at two different temperatures, 1,000 as well as 1,500. Yeah, and they believe that 1,500 probably pretty representative of the actual temperature in a thermal release situation. Yeah.
Okay.
But as I mentioned, again, they have done a quite extensive test. I did not get a chance to present nearly. Just kind of little flavor of what has been done. But anyone interested, please let us know. Yeah.
Sure. Yeah. Well, thanks a lot. Appreciate it. And a question related to the G levels that the internal modules can withstand in a side pole impact. I think this is basically, if I'm not mistaken, kind of a standard test. But any comment on the G levels that the modules can withstand? It depends on the type of module, of course. Yeah.
Right. Yeah. It's a pretty standard low case. Yeah.
Okay.
Yeah. They're used by a lot of, if not of the OEM customers.
Yeah.
And if anyone has a specific low case, that we can definitely evaluate that, right?
Yeah. I think, and it's also a function of the type of cells that are being used. So yeah, it's kind of an open question there.
Yes.
So there's a question here that says, where are the tailor welds located between the 1500 and mild steel in the tray? How do you assure flatness of the 1500 sheet?
Yeah, that's a really good question. So the laser weld, it's a pond-shaped tailor welded blunt design, and the laser weld line is at the bottom of the tray, so it does not participate, in the drawing of the wall. So and the bottom, the flatness of the bottom as well as the flatness across the entire flange were measured using CMM. So both are meet a really tight tolerance target. So plus and minus 1.5 millimeter across the entire flange. And for the bottom, I think we meet the 2.0 millimeter flatness. Yeah. Okay. For the bottom tree. Yeah. And some OEM might have interest in joining some of the cooling plate, for example, with the bottom of the tree. So it is also desirable to have to achieve certain flatness target for the bottom of the tree.
Okay. Very good. I do have two more questions on the list, and both of them are related to cost. In a general sense, I think that one of them is saying, can you share with us what you learned? And the other one is basically, can you offer rough cost comparison versus aluminum pack at, say, 200,000. I mean, these are getting a little bit specific in terms of cost, but in a general sense, what kind of how competitive are you with the current production aluminum boxes?
Yeah, that's a really good question, Hassan. So the short answer is definitely we can share with you. If anyone's interested, contact us afterwards. We can share comparable, I mean, roughly ballpark estimate, steel design versus aluminum. Our the strong feature of our advantage we have is on the cost side. So. Okay.
I'm assuming.
Yeah,
I mean,
sorry, I cannot give.
No, you're
detailed
absolutely
numbers
no.
But definitely, if anyone's interested, yeah, contact us so we can discuss for sure.
Totally understood. Yeah, totally understood. I mean, when you think about it in terms of just material cost, I think for all intents and purposes, it should be very competitive with the current design. But
yeah, and also, Hassan, as you can see, our battery enclosure, for example, all the C-STAR use a very simple, efficient manufacturing measures. Just top and bottom, top cover, bottom tray, 2 stamping parts, and then throwing some roll formed cross members, and as well as L-shaped tube, which is the first time we have tried this, and then these are all very efficient manufacturing measures. Then just to make sure that we are on the cost side, we have taken that into account in our design.
Yeah. I think, and to answer those questions for the participants, clearly, like you said, Yu-Wei, if there are specific questions and specific needs, I think Cleveland-Cliffs would be more than willing to work with you on that.
Yes.
I do not see any further questions. I think basically all the questions that I had have been covered by the participants, which means that everybody's been very much enjoying your presentation and very much paying attention. So once again, thank you very much for a great presentation. And I will just let Brian jump in. Thank you very much, Yu-Wei. Thank Miao.
Thank you.
Thank you.
Yeah, and Yu-Wei and Miao, Hisham, thank you very much for a great presentation today. Very much appreciate everyone's attendance and participation. The presentation will be posted to the American Iron and Steel Automotive website, and we will also release a copy of the recording. In the meantime, stay tuned for additional announcements about next webinars, and mark your calendars for Great Designs in Steel, May 21st, 2025. Thank you and have a great day.
Thank you, everybody.
Thank you.